All right, we're back. We are on page 7 of notes 9 of Calc C, and what we're going to do is a little bit weird. So we want to try to write a new series, and we're going to do it by using either differentiation or integration of a series or a function or whatever. We'll see what happens. So the process kind of looks like, so I'm gonna zoom way in here and then write kind of small. So what you can end up doing is like you start with a function and you're like, I don't know how to write a series for that. So then you'll take the derivative. That'll bring you down here. When you take the derivative, maybe you do know how to write a series. So you write a series for that. And then you'll integrate. So that's one option. The other option is that you start with a function and you don't know how to write a series for it. But you look at it and you're like, if I took the integral of that, I think I would know. So you could integrate. You get the integral and you're like, yeah, I can write a series. So we'll write a series. And then because you took the integral and wrote the series, you have to take the derivative to get back. So we're going to do one of these. So this would give us our series, or that would give us our series. So that's like kind of the idea. So maybe I shouldn't use equal there because that's a little confusing. Like back and forth. I don't know. One of those. Something. That's our plan, sort of. And like, until someone shows you this, I don't think it like jumps out as anyone as like a very obvious thing to do. But like, if someone says write a series for arctan, I'm like, I don't know. Let me take the derivative. So f prime of x, because the derivative of arctan looks very much like a geometric series. So this is 1 over 1 minus negative x squared. Okay, if that's the case, then I see r is negative x squared. And I can write a series for this. So f prime is going to be the sum from 0, quantity, negative x squared to the n. And then we need the absolute value of r, the absolute value of negative x squared to be less than 1. But that's actually, we've done that several times. That's just this. Okay, why is this important? Why is it important to do this? So I'm going to say, well, we know why that's important, right? Because the integral or the derivative of a series, the open interval, always the same. It could vary at the endpoint. So this, the integral, has same open interval. Could vary at the endpoints, so we have to check the endpoints, but like the open interval is going to be the same. So definitely between -1 and 1, and we'll see from there. So first, I'm going to rewrite this, like before I integrate, as -1 to the n, x to the 2n. And the reason I'm doing that is because I want to reverse the power rule on this thing, and like the whole quantity thing, it wasn't working for us. So we're going to say that f of x is some integration, constant of integration. I was going to say integration of constant of integration, n equals 0. -1 to the n is a constant multiple, x to the 2n plus 1 over 2n plus 1. Absolute value of x is less than 1. Oh, no, we don't know that yet. We suspect, right? We don't know. We actually have two things we need to do. I need to deal with C for sure. What are you doing? For sure. So how can I deal with that? Arctan. So I know that the arctan of 0 is 0. And if f of 0 is 0, that means that C must equal 0. Because if I plug 0 in for x, I'm just summing up 0. So 0 plus C has to equal 0. C must be 0. So that's good. So we know that so far. So f of x is definitely this. I don't know, am I going into the space for the other problem? Not exactly yet. N x to the 2n plus 1, 2n plus 1. Okay, so we have this. Now we got to test the endpoints. So I know the open intervals from -1 to 1 because the integral and so a series and its integral have the same open interval of convergence. could vary at the endpoints. So if I let x equal -1, I get, so -1 to the 2n plus 1 plus n is -1 to the 3n plus 1. 3n plus 1 is not like always even or odd. So that's going to alternate. And if it alternates, this converges by alternating series tests. So I'm going to assume that you know these tests and that like you can work that stuff out because it's a lot. And I don't want to do it in the video. But there are other videos if that's what you're looking for. And 2n plus 1. This is also going to converge. Wait, 2n. You know, I kind of thought it didn't converge at both endpoints, so I don't know. But this also converges by alternating series test. Conditionally convergent for both of them. So it looks like it converges at both of them. I don't know. I mean, sure. So we get this. Okay. So what should we do? Maybe we should take a look at the graph, because I feel like this video is kind of long, so I don't want to necessarily do the next one in the same video. So let's see. F of x is arctan of x. So like the Taylor, since it doesn't tell you the interval, like this isn't really very helpful, but we can do this. And that's what we got, I think. Yeah, I'm pretty sure that's what we got. So let's take a look at the graph and see if we can like see this convergence. Maybe. F of x, and then so what am I even doing? Tab. Okay, and then I want to do the summation from 0 to, let's just start with 50 and we'll see. -1 to the n, x to the 2n plus 1, and then 2n plus 1. So we're trying to see if it converges at -1 and 1, which I think, I mean, it looks like it does. I mean, if you put in, yeah, I mean, I guess it must. Alternates. You go, if n is 1, if n is 0, you get 1. If n is 1, you get 4. So it's alternate. Yeah, like, yeah, converges at the endpoints. Okay, I don't know why I'm like so skeptical of this. It looks like it converges at the endpoints. There aren't like asymptotes that are screwing it up. So I'm going to say that it converges at the endpoints with the caveat that like it's making me really uncomfortable to say that for some reason. But anyway, I'll be back in the next video and we'll do more of these. So I will see you there.